I'm very happy to introduce to you Janosz Dewberry. So he is a young postdoc, as I can say. So he completed his PhD at the University of Cambridge in the UK in 2019, and then despite the COVID epidemic, he managed to do postdocs at 4 different places. So he started out in China, of all places, Shanghai, where he did his first postdocs, and then he moved on to Cornell University. And his third postdoc was, or still is, at the Canadian Institute for Theoretical Astrophysics. But he's also at the moment visiting the California Institute of Technology, where he entered already, where he started in November last year, and where he still is in the team of Professor Jim Fuller. So Janosz is a theoretical astrophysicist with a background in fluid dynamics, and so he's focusing on problems that have to do with oscillations and tidal interactions of rapidly rotating or magnetized planets and stars. And that's also what his topic is of today. So Janosz, you have the floor, please.
Thank you, Joris, very much for that introduction. And thank you all for having me. I'm excited to speak to you all today, at least virtually. So as Joris mentioned, today I'll be talking about a field of research that I've worked in for the past few years, which is the effects of rapid and in some cases differential rotation on the oscillations and tidal interactions of stars and gaseous planets. Before I start moving on to dynamics, I'd like to just briefly run over the basic effects that rotation can have on the time-independent equilibrium structures of planets and stars. So I should first just clarify, by rapid rotation, I mean rotation at a significant fraction of dynamical frequency defined in terms of planet or star's equatorial radius. Certainly there are a large number of stars at this point that have been identified that satisfy this criterion, but we don't actually have to go outside of our own solar system. So Jupiter and Saturn both rotate at around 30% and 40% of their dynamical frequencies respectively. And this is already rapid enough to introduce some fairly interesting effects. The first of these you can actually see just by looking at these images. So you can see that Jupiter and Saturn are not spherical. They are centrifugally flattened. And so this is the first effect of rotation that I'd like to highlight, which is that if you introduce rotational velocity to your Euler equations, this modifies the mechanical time-independent equilibrium, leads to a set of equations that are not spherically symmetric and will in general lead to a flattening of the planet or star. This animation is showing the flattening of polytropic models that I've computed. The color map is showing density, and this is just for increasingly rapid rotation. The end of the animation shows what's called a critical mass shedding limit, at which the centrifugal potential exactly balances gravity at the equator. So if the planet or star were to rotate any more rapidly, it would start to lose mass at the equator. The exact mass shedding limit depends a little bit on the details of the equation of state, but this more or less comes close to the dynamical frequency that I already introduced. You can get some even weirder shapes for rotating planets and stars if you start to think about rotation that varies spatially. So what I've written out here is called a constant J rotation law. This depends inversely on the cylindrical radius, the distance to the rotation axis. And so you can see that because of this, there's a preferential flattening very close to the rotation axis. So you end up with a structure that looks kind of like a donut or a torus, but without a hole at the center. When we talk about differential rotation, it makes a little bit less sense to talk about a specific rotation rate. Slightly more relevant quantity is just the ratio between the total kinetic energy and the gravitational energy. I should mention that there are some higher order effects of rotation that I won't talk about at all today. Most notably, meridional circulation will probably result when you have baroclinic relationship between density and pressure, for instance. But I won't be taking account of those effects in the work I described today. Instead, I'd like to move on and talk about how rotation can affect the time variability of planets and stars. So given the number of astroseismologists in the audience, I don't think I need to espouse the virtues of non-radial oscillation modes. These are, of course, incredibly useful tools. They are the result of introducing time periodic perturbations to the fluid dynamic variables, in this case, the gravitational field. Mathematically, the oscillations of the basic case of a non-rotating, non-magnetized star or gaseous planet are very nice to work with for a number of reasons. First of all, they are solutions to partial differential equations that are entirely separable in terms of spherical harmonics. So that means that you can describe the angular part of the eigenfunction of an oscillation of a non-rotating planet or star entirely in terms of a single spherical harmonic with degree L and azimuthal wave number M, and just multiply that by a radially dependent function that you have to compute numerically. Also, for non-rotating planets and stars, there's a relatively small number of different types of oscillations to think about. These can usually be broken up into two main categories of P modes and G modes that have restoring forces from pressure and buoyancy in the fluid, respectively. The plots that I've included on this slide are showing the structure and also the three-dimensional variability of a so-called fundamental mode, or F mode. These are somewhere in between P modes and G modes. They're physically the most similar to surface gravity waves that you'd encounter in the deep ocean. And as we'll see, they are quite important to observations of Saturn. Rotation can significantly complicate the process, both of calculating oscillation modes and also characterizing and interpreting their results. This is because rotation introduces both a Coriolis force that directly affects oscillations, and there's also an indirect effect from the centrifugal flattening of the equilibrium structures that I already introduced. Both of these forces break the spherical symmetry of the oscillation equations, so it's no longer possible to exactly describe the eigenfunctions of an oscillation of a rotating planet or star in terms of a single spherical harmonic. What you can do, and this is an approach that a number of research groups have explored at this point, is expand the eigenfunctions in terms of a sum over multiple spherical harmonic degrees. So you end up with expression for your mode that involves multiple surface harmonics, each multiplied by their own radially, or in this case, quasi-radially dependent coefficient. The animation on the right here is showing the result of putting all this together. This is the propagation of the same F mode from the previous slide, but in this case, I've computed it for a near critically rotating polytropic model. In addition to altering the characteristics of singular oscillation modes, rapid rotation can also modify the overall structure of oscillation spectra. So this selection of cross sections, these are vertical slices along the axis of symmetry for G modes that I've computed for a non-rotating polytropic model on the top, and then for a somewhat rapidly rotating polytropic model on the bottom. And this is illustrating a fairly well-known process by which rapid rotation can mix together the eigenfunctions of G modes that in the non-rotating regime have very closely spaced frequencies. And on the other side, in the rotating model, you get a spectrum of modes that again has very closely spaced frequencies, but has quite a different angular structure in their eigenfunctions. In addition to altering the oscillations that would already be present in a non-rotating planet or star, rapid rotation can also, well, really any rotation, can bring entirely different types of oscillations into play. So these cross sections are again slices along the rotation axis with the color map showing density perturbations for what are called inertial oscillations. These are oscillations that have a restoring force provided by the Coriolis, so they're fundamentally associated with the rotation of the fluid, and they generally occupy a low frequency regime of parameter space. And as we'll discuss later, this makes them somewhat important to tidal interactions. Lastly, I just want to mention that rapid and differential rotation can also in some cases lead to instability. So this animation is illustrating the growth of what's called a dynamical bar mode instability. If you think about the rotation profile, the constant J rotation profiles for differential rotation that I introduced earlier, it's been known for some time that this leads to F modes that are dynamically unstable, so they grow very rapidly. And so clearly the growth of this F mode is going to alter the stellar structure and rearrange angular momentum unless it's altered. And so this is just to say that just because you have a rotation profile that satisfies your time-independent fluid equations, it's not necessarily going to last for a long time. All right, so I'm now going to move on and talk about some actual astrophysical applications of this theory that I've introduced. And I'm going to start by talking about some work that I've done that is the broader goal of trying to use Saturn's rings as a very large seismograph. Motivation for this work comes from a few observational difficulties when it comes to Saturn. So first of all, it's in general pretty difficult to probe the very deep interiors of gas giant planets, even in our own solar system. This cartoon is illustrating schematically the basic structure that planetary scientists have thought that dominated in Saturn for quite some time now. This mainly consists of two components, a big envelope that's fully convective, composed of mostly hydrogen and helium gas, and then beneath that some core of rock and potentially ice. Whether or not this core exists is somewhat important for theories of planet formation, but actually confirming its existence is very difficult. So even though the satellite Cassini, which was in operation for a number of years around Saturn, collected incredibly precise measurements of Saturn's external static gravity field, this actually leads to still leaves a fair amount of degeneracy in the possible central densities for the planets. That's illustrated on this plot on the right that shows a posterior probability density distribution for possible density profiles, just given the constraints provided by the Cassini gravity data. So it'd be great if we had some alternative ways to look at Saturn's internal structure. Additionally, it's also fairly hard to measure Saturn's rotation rate, at least with the approaches that have been used primarily in the solar system. This is basically just because Saturn's rotation axis aligns almost perfectly with its magnetic axis, and it's the misalignment between these two axes that's been used to measure the rotation rates for most of the other planets in the solar system. Fortunately, Saturn has this very large set of rings, and these turn out to be quite useful for probing both of these intrinsic properties of the planet. So the basic idea behind Saturn ring seismology, which is also known as chronoseismology, is that a subset of Saturn's non-radial oscillations produce some external time periodic and spatially varying perturbations to Saturn's gravity field. And these in turn can excite waves in Saturn's rings. Now, importantly, these waves are excited at different radial locations in the rings, depending on which oscillation mode is involved in exciting the wave. So this was a mechanism that was proposed back in the 90s. It was tentatively confirmed by observations from Voyager as it passed Saturn, and then was more conclusively confirmed by observations from Cassini. Most of the waves in Saturn's rings are identified through a wavelet analysis of optical depth measurements that Cassini takes during occultation events. These are events where the satellite looked at starlight shining through the rings. And so at this point, there's about 30 waves that have been detected in Saturn's rings that can more or less unambiguously be identified with being excited by Saturn's internal oscillation modes. This plot summarizes most of the data. So on the y-axis, this is the azimuthal wave number. This is the M for both the waves in the rings and also the oscillation mode that is involved in exciting them. On the x-axis, this is the distance from Saturn's center. Again, this is a proxy for the frequency of the oscillation mode in Saturn that is involved in exciting the waves. The open boxes here show predictions for wave excitation by Saturn's F modes for a fully convective model of the planet. And then all the filled markers show actual wave detections. There are two main types of waves that are excited by Saturn's internal oscillations. There are, first of all, density waves. These are excited by modes in Saturn that have even symmetry with respect to Saturn's equator, so even L minus M. And then also bending waves, which are ripple-like corrugations. These can be excited by Saturn's oscillations that have odd equatorial parity. So the solid and dashed tracks here show F modes with even and odd equatorial parity that would excite these different types of waves. So as you can see from this data, the data more or less matches predictions for excitation by F modes for a large number of these waves. In particular, these waves that have relatively high degrees and azimuthal wave numbers are more or less, it's pretty clear that they're excited by F modes. And these turn out to be really useful for probing Saturn's rotation, at least in its outer layers. On the other hand, you might have noticed that down here with m equals 2 and m equals 3, there are more waves than can be explained by Saturn's F modes alone. And so this provided pretty strong evidence that there are some additional oscillations in Saturn's interior that are producing some large external gravitational perturbations. The leading explanation for these additional waves is that they're excited by internal gravity modes in Saturn, associated with some stable stratification in its deep interior. And so this is really exciting because it provides a potential window to learning more about Saturn's deep internal structure. Just last year, my collaborators, Chris Mankiewicz and Jim Fuller, used specifically the m equals 2 data. So they showed that if you identify these m equals 2 waves with an F mode and the 2 lowest order G modes, that this leads to a fairly strict requirement that rather than having a solid core of rock and ice, Saturn's core is actually fuzzy. So they showed that this identification leads to the requirement that Saturn have a really shallow gradient in composition that leads to a very wide region of stable stratification, and this overall picture of a extended fuzzy core, which is interesting because that flies in the face of the historical picture that I painted earlier. Instead of a solid impermeable core, it looks more and more like Saturn is just gaseous all the way down. There is some caveats though, in that Jim and Chris encountered some difficulty in actually fitting these lowest frequency m equals 2 waves that are furthest to the right on this plot. And they also had trouble explaining the very close frequency spacing, both for m equals 2 and m equals 3. You can see there are waves that are spaced very close together in the rings, which means they're excited by modes that have very similar frequencies. And so a potential explanation for these difficulties that they encountered is that they used an approximate so-called perturbative treatment of Saturn's rapid rotation. As I mentioned, this is around 40% of the breakup angular velocity, so this stands to omit some fairly important effects. Additionally, on top of Saturn's rapid bulk rotation, it also has some fairly strong atmospheric winds. So the plot on the left here is showing wind speed as a function of latitude observed on Saturn's surface relative to some assumed background rotation rate. And the cross-section on the right is showing the differential rotation that results from this after you make some assumptions about how that wind decays inside Saturn. And so last year, I worked with Chris and Jim, as well as some collaborators at Cornell, Dong Lai and Wenrui Zhu, to take into account these these higher order effects of Saturn's rotation. So we used what is, to my knowledge, the first complete treatment of Saturn's rapid rigid rotation in realistic models of Saturn's interior. We used the models that came out of Chris and Jim's work. And we also use an approximate so-called perturbative treatment of Saturn's atmospheric winds. First result that I'd like to highlight from this work is that we found that the differential rotation in Saturn's atmosphere has a measurable impact on Saturn's high degree F modes. So the plot on the right here is showing the percent frequency shifts for F modes as a function of their azimuthal wave numbers, m, and also degrees are indicated by the inset here. And for context, the observational uncertainty on the frequencies of the waves detected in Cassini data is around 0.01%. So even though these changes in frequency are quite small, they're still well outside the observational uncertainty. So this presents a real opportunity to learn to use Saturn's high degree F modes to place constraints on the spatial variation of the differential rotation in Saturn's interior. And this is something that Chris and Jim and I are actively working on. In this paper, we also took a look at how Saturn's rapid and differential rotation can alter mode mixing. Specifically, we found that the full effects of Saturn's bulk rotation and also this differential rotation can enhance the mixing of F mode and G mode eigenfunctions, producing interactions like the one that's indicated on the bottom cross sections on this slide here. This is a 3-mode interaction. It involves 3 modes that all have very similar frequencies. And somewhat interesting structure. So on the surface, you can see that all three of these modes have a structure that looks kind of like a sectoral F mode, but then in the deep interior, they have a higher degree structure that looks more like G modes with various spherical harmonic degrees. And so this is somewhat relevant to the very closely spaced waves that we saw in the observations here. In particular, we showed that this triplet of m=3 waves could ostensibly explain an observed triplet of waves in the rings. And we also found that a complete non-perturbative treatment of Saturn's bulk rotation produced a lot of these rosette mode oscillations that could potentially be involved in explaining this doublet of m=2 waves. The last point I want to mention from this paper is that we found that a very small amount of asymmetry that is actually present in Saturn's zonal winds can mix together oscillations that have different equatorial parities. So the net result is to produce oscillation modes that are equatorially asymmetric. They're neither antisymmetric nor neither odd nor even with respect to Saturn's equator. And so this is observationally very interesting because this type of oscillation has the possibility of exciting multiple density waves and bending waves at the same time. And this is kind of cool because the density and bending waves are excited by different resonances. So this type of mode would excite a density wave potentially around here, and then at the same time, a bending wave out further in the rings. And this extra bending wave is not something that observers have looked for before. So this is an interesting possibility that I hope to hear more about in the future. I am still actively working on Saturn ring seismology. Chris and Jim and I just recently submitted a paper in which we looked at we took a more complete look at the effects of differential rotation on Saturn's oscillations. Just to give a preview from this paper, one result that's come out of this is that we found that including a complete treatment of differential rotation in Saturn's atmosphere, specifically the way that this differential rotation alters the centrifugal flattening of the equilibrium structure leads to much stronger mixing of F modes with specifically high degree G modes. So for instance, on this plot here, the blue and green lines show calculations with just rigid rotation or with the approximate treatment of differential rotation that we used last year. Whereas the orange lines plot modes that we computed with a full and non-perturbative treatment of Saturn's differential rotation. And so you can see that there's a several orders of magnitude enhancement in the gravitational perturbation for specifically a higher degree G mode. So this is interesting because it makes explaining at least some of the fine splitting observed in the rings a little easier. Okay. Lastly, in the last few minutes of my talk, I just want to talk about some work that I published a few months ago that is focused on the tidal interactions of rapidly rotating planets and stars. Again, this is work that is motivated most directly by observations of Jupiter and Saturn, but a lot of it is fairly general. So I'm considering just a basic physics problem in which we have a primary fluid body that has some spin angular velocity and is orbited by a massive satellite. This massive satellite will introduce a perturbing gravitational potential that in the simplifying circumstances where you can treat the satellite as a point mass, this potential can be a point mass that's on a circular and coplanar orbit, I should say. You can expand the gravitational potential of the satellite in terms of some multiple expansion coefficients that are known and a time dependence that involves this tidal forcing frequency. Here, omega O is the orbital frequency of the satellite or the mean motion, and omega S is the spin angular velocity of the primary. In general, this perturbing potential will lead to fluid motions inside our primary fluid body, either the planet or star. And these will manifest mainly as a tidal bulge that points more or less towards the satellite as it orbits. These fluid motions will in turn lead to density variations and induced external gravitational perturbation from the primary fluid body. We can in turn expand this in its own multiple expansion with its own expansion coefficients. And then the purpose of so-called potential love numbers or tidal love numbers is to provide a transformation between the coefficients in these two multiple expansions. There are a few different ways that you can define love numbers. The one that's observationally motivated for planetary sciences is to just define them as the ratio between coefficients that have the same degree L and azimuthal wave number M. And I should say that these love numbers, they're first of all frequency dependent. They depend on this tidal forcing frequency, and they're also complex valued. The real parts of the love numbers tell you about the shape of the tidal bulge, whereas the imaginary parts tell you about a phase lag from any dissipation in the fluid. So last year I worked with Dong Lai to calculate these tidal love numbers for a large number of polytropes rotating at up to around 90% of breakup. Basic approach that we took is to treat the oscillation modes of these polytropes as driven harmonic oscillators with the driving provided by the tidal potential. This is a fairly well-trod theoretical territory. And so this plot here is illustrating a selection of love numbers as a function of orbital frequency on the x-axis. And the main result from our paper is that you can actually reproduce this plot fairly closely just with some analytical formula that we provided for the relevant properties of the most important modes to the tidal response in our paper. But I do want to just highlight a few extra results that came along with our work and are apparent on this plot. So first of all, you might notice on this log-log plot, there's a pretty clear power law for at least some of the love numbers. And this is as the orbital frequency of the satellite is going to 0. That's kind of surprising because the orbital frequency of the satellite going to 0 means that the satellite is moving infinitely far away. So you wouldn't expect the response to be really strong in that limit. But this actually matches predictions from some nonlinear calculations and also actual observations made by the spacecraft Juno. So clearly there's something going on here. And so Dong and I showed in our work that this blow up of some of the love numbers, specifically these are love numbers that are tesserail, part of the tesserail response. They have degrees L that are greater than the azimuthal wave number M. This is a direct result of centrifugal flattening that can happen even in a very moderately rotating case. So in this case, this model is rotating at about the rotation rate of Jupiter, so 30% of breakup. I won't go too much into the details of why this happens, but basically you have a driving of the tesserail response that is dominated by more and more by the sectoral part of the tidal potential. And so this leads to dividing a moderately sized number by a really small number. And so you get this blow up that has a fairly predictable dependence on the orbital frequency. One other feature that you might have noticed on this plot are these spikes. These are resonant interactions in which the tidal forcing frequency comes very close to the natural frequency of, in this case, inertial modes. This is potentially interesting because it can lead to, oh, sorry, I skipped a slide there. It can lead to a tidal response that involves a higher degree structure. So this is a different shape for the tidal bulge than what I showed earlier. And so I've kind of exaggerated the situation by putting in a very massive satellite and putting this very close to resonance with this particular inertial mode. But this, again, is also somewhat consistent with observations. This type of resonance would help to explain an outstanding tension between numerical calculations for, in particular, K42 and observational inferences that have been made for Jupiter by Juno. I will finish there, leave you with some takeaways. Thank you very much for your time. I'm happy to take any questions.
Thank you, Janosz. Very interesting. Okay, so if anyone has any question, please mention your name in the chat and I will call you out. Perhaps I can start with a question of my own. So you may have said it, but maybe I missed this. But what's the amplitude of the oscillations of Saturn?
Yeah, so that's a really good question, and that's unfortunately something that's quite difficult to. Well, it's not necessarily difficult to constrain, but it's difficult to explain. So the waves in the rings, if I can just go back to the observations here, the waves in the rings they're detected with specific optical depth variations. And so this means that you can put at least some constraints on the amplitude of the mode in Saturn that excites them. The process of actually exciting the waves by a mode in Saturn is fairly well worked out. There's a pretty clear torque that is applied at a Lindblad vertical resonance. And so from looking at the waves, you can tell what the amplitudes of the oscillations in Saturn are. It's a little difficult to tell what the actual distribution of energy among modes is. And so this is the main thing that I've struggled with actually, is that you can have G modes and F modes that are rotationally mixed. So they have various surface gravitational perturbations. and you can the approach that I have taken and other people have taken at this point is just to anchor everything in terms of the F modes and say, okay, we know the F modes are explaining the waves in the rings, and then we assume that there's some energy equipartition between the modes. This is reasonable for at least the high degree F modes, or sorry, the medium degree F modes. And then after that assumption of energy equipartition, you can come up with some amplitudes for the G modes. But it's entirely possible that you could have G modes that are excited to much larger energies than the F modes. And in that case, actually figuring out which modes are involved in the excitation process is kind of difficult, because you for different G mode energies, you'll have a different surface amplitude of the gravitational perturbation. For instance, for these calculations, I have basically assumed energy equipartition between the modes. But that's not necessarily a reasonable assumption. That's certainly something that could be revisited.
And suppose that you assumed an equipartition. What's then so?
You're right. So for a specific number, they're about meter size displacements on Saturn's surface.
Okay.
Sorry, I gave a very complicated answer to a very simple question. Sorry.
That's okay. Okay, good. Thank you. So I see that also Dominic has a question, please.
Hi, Janosz. Thank you for the excellent talk. Very, very interesting. Can I drag you to stars, even though these planets are very interesting?
Yeah.
So something that we seem to see in hydro simulations of stellar interiors is there is a strong coupling between the gravity waves and the F mode frequencies. And there seems to be a resonance and an energy deposition of these waves into the F mode frequency. But we don't tend to see the F mode frequency in your typical dwarf B-type star, right? So I'm just curious, what your view on this is, given your experience with the F mode frequencies. Is there some sort of extra physics that's damping the F mode in real stars of why we don't see them, or is the simulations maybe over predicting that resonance somehow?
Well, I'm not sure about the simulations. I think the observations of F modes in Saturn is actually kind of consistent with not seeing them in stars. Like I mentioned, these are meter-sized displacements, so they're actually pretty small amplitude modes. And so I didn't mention at all, but there are some detections of potential detections of P modes in Jupiter and Saturn that would have much larger amplitudes. These are somewhat contentious, which is why I didn't mention them. Basically, the only reason that we see the F modes in Saturn is because they have a large gravitational influence relative to their mode energies. So even though the F modes have really small mode energies, they have an outsized gravitational influence, and it just so happens that their resonances fall within the rings. And so there's not really much hope of actually detecting these F modes just by looking at Saturn or by measuring the gravity fields directly. So I don't think, I guess I wouldn't necessarily be surprised that you don't see the F modes in stars. I don't really know about this energy deposition into F modes from G modes, so that does sound really interesting.
Okay, so the external factor is the driving thing here. So that's interesting to look for example, the binary stars, for example, or maybe these B stars have planets and they've not been detected, for example.
Yeah.
Okay, very interesting. Thank you very much.
Thank you.
Okay, then we go to Connie.
Yeah, hi, Janosz. Thanks a lot for an interesting talk. I was wondering if you could elaborate a little bit more on how you numerically treat the case where you apply wind, because there's dynamics there. Is that stationary? Is that expanding? How do you do that in your codes? Because you stitch that probably to an interior, and does that change in time or not? Could you say a little bit more about that?
Yeah, absolutely. So this profile of the winds that I've plotted on the top here, this is actually fairly time steady. So this is steady over time in Saturn. It may change a little bit. For the most part, this remains. This was what we saw 10 years ago, and it's still what we see on Saturn. So this is more or less an equilibrium differential rotation profile on Saturn's surface. In the paper that I worked on last year, we basically treated this differential rotation perturbatively. So we computed, with a degenerate perturbation theory. So we computed the oscillation modes of the rigidly rotating models of Saturn that Chris and Jim put together. This is with some realistic internal structures for Saturn. And then we use those as a basis and that we couple together with the differential rotation profile from that's actually observed from Saturn. On top of that, we made some assumptions about how that wind decays with depth. This is not a formally rigorous way to do things. So first of all, there's some difficulty. So you don't have the same Sturm-Liouville set of modes when you compute oscillations for a rapidly rotating planet or star that is centrifugally distorted. So you don't have the same guarantees of a complete basis that will converge exactly the way you want it to. We also, so in this preliminary work that we did last year, we did not include the changes in density and pressure that would be associated with this kind of a flow. So we just looked at the effects of the velocities. We basically just looked at the effect of the Coriolis force from this differential rotation on the modes. More recently, the work that I just introduced at the end of this section, in this case, I have actually done everything completely consistently in that I've put in some differential rotation profiles that I self-consistently compute the equilibrium structure of the planet. For this case, I've done some simpler models. I've just been looking at polytropes. And so then for the actual numerical calculations of the oscillations, because I've self-consistently computed the equilibrium structure, including density and pressure variations associated with the differential rotation, I have a full set of oscillation equations that I can just solve directly. And so that's what I've done for this more recent work. And that's the direction I'd like to move in the future.
Okay. I would need to think about how to translate that to stars again. Because there the atmospheric winds are much more dynamical.
I see. Yeah, they change in time a lot.
That's the trigger of my question. Okay.
I see. Yeah, that makes sense.
Thank you.
Thank you.
Okay, I have a question again for myself actually. Do you need a Cassini-like spacecraft to observe these things, or can you observe it as well from Earth?
Yes and no. For observing the ring waves, yes, you do need a Cassini-like spacecraft. So I mentioned some somewhat contentious potential observations of modes in Saturn and Jupiter, or P modes in Saturn and Jupiter. These, at least some of the potential detections were made with Earth-based instruments, so you don't necessarily need a Cassini-like spacecraft. But again, those are not settled observations.
Right. So at the moment, we don't have any perspective yet for Uranus and Neptune.
Correct. Yeah. But that is, I think, a focus over the next decade with missions out there, and there are people who are looking at Uranus and Neptune seismology.
Okay. I see a hand raised of Dominic. Is that on to ask a question or?
Yes, please.
Okay,
so Joris, you triggered a question in me. So I don't know these detections of the P modes in Saturn. So apologies for that, Janosz. How were they made?
I am not incredibly clear on the details. So the paper is Gualme 2011. So this is it was with an Earth-based telescope. I'm not sure which one. I think they were just looking at. I can't remember if I think they were just photometric detections.
Would you expect to see, is the amplitude of the signal high enough that you'd expect to see it in, for example, spectroscopy?
I think that's what a lot of people are arguing about.
Okay.
Yeah, I think what people argue about is that the amplitudes that you would need for the observations are incredibly large. So P modes that have displacements that are, a significant fraction of Saturn's radius, and so it's kind of hard to envision that actually being the case. But again, I'm not incredibly familiar with the observations there, so sorry, I can't help you too much.
Okay, you've given me some reading. That's good. So thank you.
Okay, thanks. Anyone else have a question for Janosz? If not, then I would like to thank Janosz again. Thank you very much. So Janosz will actually visit Leuven, to visit the TESS conference. So if you have any more questions or want an opportunity to discuss with him, you can do so in early July. So, okay. So